Top of the morning, ladies and gentlemen, and welcome back to Nafta College Webinars. I would like to welcome everyone who is on stream with us right now. Let's make a quick sound check to make sure everything is working. There should be a chat box to your right side. Tell me if you can hear me. Okay, perfect. So today here with me, I have a guest from Toyota System, Dr. Andrei Arbuzov, who has an exciting presentation packed all for you guys. Dr. Andrei Arbuzov is a CTO in Toyota Systems, a company providing novel well completion solutions globally. To date, Dr. Andrei Arbuzov has over 11 years of experience in oil and gas industry, and his experience and leadership has been focused on developing and delivering cutting-edge technologies in this field. His technical expertise include permanent downhole monitoring systems, intelligent completions, logging tools, and software. He also has a lengthy academic career, having published over 22 papers and having 4 patents, having done a tremendous contribution to petroleum society as a whole. Now, before we begin, let me give you 3 short tips on the format of today's webinar. If for some reason you're not here with us right now, don't fret. The stream will be saved on our channel where you can rewatch it again. Throughout the webinar, please feel free to leave your question in the chat box. And after the presentation, the speaker will answer all posed questions. Bear in mind that we have around 15 minutes for that part. So in case your question was not answered, they will be always discussed later at Nafta College Forum. So without further ado, let's begin. Andrew, a word to you.
Yeah, thank you, Artyom. Good day to everyone. Let me share the screen. I hope you can see my presentation on my screen. Just wait maybe for like 30 seconds more. So I think we can start our presentation. So today I would like to discuss with you flow control devices for the smart wells. Unfortunately, you cannot ask me the questions directly during the presentation. You can only write down some questions in YouTube. Maybe because of the COVID, you know, it's too risky to ask the questions directly in Zoom. So let's start our presentation. Let me just mention again that as I was working in TGT oilfield services for like 10 years and now joined the Toyota System company, focused on intelligent completions. So today I want to discuss with you the most popular flow control devices for smart wells. We will start with ICD, the most simple one, the beginning, the basic one, inflow control devices. Then we will discuss the AICD, autonomous inflow control devices, which is a little bit more complicated from the technology point of view. Then go to the hydraulic flow control valves, which you can open and close at any time. And then go to the most advanced full electric valves. So let's start. What is the challenge, the main challenge with the horizontal wells? So the horizontal wells is a very good thing because it increases the production compared to the vertical well a lot. But if you have any problem in a horizontal well, it's even much more complicated than in vertical well. For example, there are a lot of wells, horizontal wells with a long lateral. It could be like 1,000, 2,000, 3,000 foot or more. And some of them are with open hole. So if you have a carbonate reservoir, you have open hole, and this is your completion. This is your well sketch. 958 casing, then 7-inch liner, then 6-inch open hole. This is a very popular completion in the Middle East, for example. So the main problem is that the lateral is quite long. It's 1,000 foot, and some of the zones are low permeable zone, let's say 10 millidarcy, and some zone are high permeable zone, so it's like 100 millidarcy. So if you just produce from this well, of course you will produce much more, and mainly from the high permeable zone, and you will produce just a little bit from the low permeable zone. So finally, when the water breakthrough will happen, this high permeability zone will be depleted, and still you have a lot of oil unrecovered in a low permeability zone. Your recovery factor will be very low for the low permeability zone. Another big challenge, especially in carbonate reservoir, are fractures. So if you have a fracture and suddenly this fracture reach the water-bearing formation below, you will have a water breakthrough, or it could be a gas breakthrough. And then this only fracture may produce like so many water or gas that your well will not produce oil anymore. And it is a big problem how to do workover in this well, how to isolate this fracture and do the water shut-off. This is very, very complicated, because imagine you have a fracture which is hundreds of meters, or like 1,000 foot far away from the well. So imagine how many some isolation gel you need to inject to stop the water coming from this fracture. And still the water can, even if you block this fracture with the cement and some gels, then the water can come again through some and find the path. Especially if you have a gas, it's even more complicated. So you need something more advanced with your well completion to manage your well. And this is the main issue for the industry with horizontal wells right now. The water and gas breakthrough, the non-uniform production, so you mainly produce from high permeability zone and almost nothing from the low permeability zone. So finally, the oil recovery factor is very low, and the associated oil production costs are very high. So with the current prices for oil, many wells, they are not profitable at all, because the water and gas break through, and your well is like 99% water cut, and it's not profitable at all. You need to stop the water or gas production and then produce from some other zones. This is the main challenge, how to do this. So one of the solution which was commercially started in 1997, so quite a good time ago, more than 20 years ago, is the concept of smart wells. So you can divide the well to sections. So remember your well sketch, like 958 casing, 7-inch liner, and then you have open hole, and you install, for example, tubing or liner with the packers. So you divide the well to sections. On the screen right now, you divide the well to 3 sections only. And in each section, you have a flow control device. So it could be a simple hole, or it could be some valve which you can open and close. But the main idea is that if you have a water breakthrough in the section number 2, for example, through the fracture, then you can just close this flow control device to stop the water production or gas production, and still produce from the section number 1 and section number 3. So your well is manageable. You can manage your production. You can close some zone maybe choke them. For example, you can choke the zone with like high permeability and pressurize low permeability zone to produce. This is the general idea. And let's discuss which flow control devices are like the most popular now in the industry. Of course, there are a lot of benefits. So first, no need to do a water shutoff workover. The water shutoff workover in general costs something like 30 to 50% of the well price. So if your new well, let's say somewhere in the Middle East, costs like 10 million, then you need to pay like 3 million to do the water shutoff workover to stop the water coming from a zone or fracture. And these workovers are not really successful. Usually only 1 out of 3 workovers are really successful, and 2 of them are not successful. So the water or gas find a way to go to borehole, and you produce still a lot of water or gas. So in this case, with the smart well, you don't need it. Yeah, you just close the valve or flow control device across this watered section, and still produce from 2 other sections, or you can divide it to more sections if you want. No need for PLT really. Yeah, so if you have this well, you have, for example, pressure and temperature sensors and maybe water cut sensors or some other way to measure the water cut, then you don't really need a PLT. Yeah, you have all the data in real time at surface. Even sitting in your office, you can install the modem, send the data to your office, to your PC, and you're sitting in the office. No need to go to the well site, no need to do any PLT. You just monitor your well in real time. You can close all the sections, for example, except one, to see what kind of production is coming from this section, like section number 1. Yeah, for example, it's soil. Okay, let this section produce more. Then you open the section number 2 and see at surface, okay, almost 100% water cut. Let's close this section. Section 3, again oil. Let's keep it open. So this is how it works, and you don't really need to log this well, which is also cost effective. Uniform production profile. This is another big benefit. Maybe this one is the most important, because the modern wells are quite long, and usually based on statistics and PLT in the horizontal wells and some other logging, only 30% of the well is working. So you drill like 3,000 foot well, and only like 1,000 foot produce oil, yeah? And other zones are not producing at all. This is a problem, and for example, if this section is high permeable, you can not close the section, but choke it a little bit, yeah, and fully open the section 1 and section 3 with low permeability, like 10 millidars, yeah. So you will uniform the amount of fluid coming from each zone, uniform the production, and increase the oil recovery factor. So finally, you will increase the recoverable reserves, because some of the reserves now are like not profitable because of too high water cut, etc., and extend the well production. Yeah, usually one of the clients shared with me some data. They drill like 500 horizontal wells, and in general, after 1 year, the water cut was close to like 60%. After 2 years, it's more than 85. So like the well life is like 2-3 years only, but according to the plan, it should produce oil for like 10 years, but they cannot afford it with the current oil prices. And another nice benefit is remote control and real-time production optimization. So you can sit in the office, no need to go to the well site, which is additional costs. You just open and close devices remotely and monitor your production and optimize it. And if you can see the water cut, high water cut from this well, you just close some section to stop the water or gas production, and that's it. especially with the current COVID situation, where it is so difficult sometimes to go anywhere. This is very actual, yeah, just remote control, and that's why it's so popular now. So let's start with the first device, inflow control device. So the inflow control device is actually a hole, yeah. So this is a real photo of some ICDs. So this is a hole with some ID, yeah. And if you have like 10 millidarcy here and like 50 millidarcy here and 100 millidarcy here, to uniform the production profile based on your model and on your open hole data, you can put like very small hole, let's say quarter-inch hole here, half-inch hole here, and like maybe 1-inch hole here. Yeah? And finally, you uniform the production. This is the main idea. It could be applicable for both offshore and onshore wells. You can, but the issue is that you can select the choke size, the optimal hole size, based on the modeling, on your open hole data. And we know, and maybe you know better than me, how accurate are our data, yeah? Especially if we are talking about permeability. We don't know really the permeability with such an accuracy. Yeah? It could be different, maybe 2-3 times different. Yeah? So the exact size of the hole is a very big question. So you can install it, and then so you spend a lot of money to install these ICDs, and then finally you understood that your initial data and modeling and open hole was not very accurate in terms of permeability, and you need to change the size of the hole. But this is again a very expensive workover, yeah, and this is a problem. So this is the main maybe problem with ICDs, and still they are so popular because still the clients, you know, they know that some zones are very high permeable zones, you need to choke them, and some of them are low permeability, no need to put any restriction across this zone. So that's why, and the price is like relatively cheap. Still, it is, you will pay a lot, yeah, to install all of these devices in a real well, do a workover. But still, they are very popular. Maybe the most popular devices for flow control, mainly because of the price. Another issue is that these holes sometimes are quite small. And after like 1 year, 2 years of production, because of the scale can block the small hole completely. So after a couple of years, you may not produce anything from the zone just because, you know, some sand scale block the zone completely. And this is an issue, yeah. This is a big issue. So the technology is simple and relatively cheap. This is the advantage. You can somehow uniform the production based on your modeling, and it depends how accurate your modeling and your open hole data. But you cannot change it. Yeah, if you find that the water came from the zone number 2, usually you cannot close it. For some ICD, there is an opportunity with the cold tubing operation to close it. But again, you will pay for the cold tubing a lot. And sometimes you cannot do it because of the scale and you cannot move it. So there are a lot of issues with ICDs. This is what the client told me. And let's go to the more advanced thing, the autonomous ICD. So the whole idea is that based on the different viscosity of oil and water, for example, or oil and gas. So there is a laminar flow element, like a flow loop, and some small part of the flow, incoming inflow, goes through the loop. So if you have like high viscosity oil, then it can hardly go through the loop, yeah. And you see this channel, so it goes through the loop and then pushing back this this metal part, yeah, this thing. So if there is oil, this force is very small, yeah, because the high viscosity oil cannot go through this very thin laminar flow element. But if you have a water, the viscosity is low, it can quickly go through the loop and then automatically close this device. Yeah, this is the whole idea. But the problem is that you first of all, you are not sure about your AICD position, AICD positions. Is it closed or opened now? You don't know really. It's based on the viscosity. So for example, in the Middle East, the viscosity of oil sometimes is very similar to the viscosity of water. It could be like 0.3 centipas for both. In this case, this concept doesn't work completely. Yeah, you need some very big difference between oil and water or oil and gas to make it work. And another problem is that, for example, with the current oil prices, you want to close this AICD when the water cut is like, let's say, like 70%. Yeah, because like 80-90% is not profitable. Yeah, you want to close it. Even if you somehow tune this device to automatically close at like 60% water cut, and even if it works, yeah, tomorrow when the oil prices like could be higher, yeah, and you still want to produce from the zone, you cannot do anything. Yeah, it's closed and you cannot open it. You block the resource, yeah, forever. So you need to either drill a new well or whatever. So and you don't need it. Yeah, the client need to open and close a section in time. So today the water cut is like 50% from the section number 2, and from the section 1 and 3 it's like 10% only. You want to close the section number 2. Yeah, and then tomorrow all the sections are high water cut. You want to open this section 2 again to produce more. With this AICD, you don't have any control. Yeah, so maybe it's open, maybe it's closed. You don't know. And if you really want to open it or you really want to close it, you cannot do it. It closes automatically based on some different viscosity, which is not really efficient. Yeah, so this is a problem. And again, no pressure and temperature data, of course, in this AICD. So it's just a mechanical device. The price is medium, so it's more expensive than ICD. Maybe less expensive than some other valves. But the main issue that you cannot control it. Yeah, you cannot open and close it when you want it. That's why it's quite risky to put this AICD in your well. So the more advanced flow control devices are valves. Like the first inflow control valve was hydraulic one, made by Halliburton, and 1997 they already installed these valves. So the good thing is that you can close and open the valves when you want it. Yeah, you need you have some channel, hydraulic line, and you can apply some pressure at surface to open it or close it. Sometimes it could be several positions. Yeah. The problem is that you need a lot of additional hydraulic lines. So if you have like 3 sections or 10 sections, you need like 3 lines or even more lines. And each line is a small tube. So finally, I got the feedback from the client that I'm not very happy with the reliability of such devices. So they're quite expensive. So this is a real smart well. Yeah, you can open and close the zone, but it's quite expensive and it's not very reliable because of so many hydraulic lines. If you damage any line, it's not working. There is some oil inside the line. If you have some dirty in this oil with time, so becoming like some sand particles inside, it can block the valve. So the client told me that it's not really reliable. And the size of the valve is quite big. So Usually the client asking for like accessibility. So there is a through hole through the valve. And the size of the valve, the smallest one which available on the market for the hydraulic valves are like 4.7 inch OD. So it's quite big. Yeah, there are so many valves with 4.5 inch liner. So you cannot put it inside 4.5 inch liner, this valve. You can only put it as a part of your completion, and the size of your open hole or cased hole should be quite big. Most of the valves starting from 5.7 inch. So you need a really like 7-inch cased hole, or maybe at least 6-inch open hole, maybe a bit more, to put this valve inside. So, and these are mainly offshore market, finally, because the price is high. We will discuss the prices a little bit later on. The OG is big. So for many onshore wells, maybe for 50% of the onshore wells, or maybe more, these valves are not applicable, unfortunately. And the reliability is a big question. Yeah. So the most advanced valves are full electric valves. So you have a cable. Usually it's tubing encapsulated cable with a metal pipe inside. And you can install as many valves as you want, like 10 valves or 20 valves, whatever, using only one cable. Yeah, it's digital signal. You just send the signal to the valves number 3 with this ID, open or close or choke. This is the most advanced one. You have pressure, temperature data, water cut sensors to control the fluid. Unfortunately, it works for this particular valve up to 30% water cut only. So I think it's based on the capacitance. And when the water cut is more than 30%, it's like off scale. So it cannot distinguish between like 30% water cut and 50% water cut, or even 100% water cut, which is not very good, yeah, for online control. But the main problem is that these valves are extremely expensive, really. So we will discuss the prices. The prices is more than $1 million per section. So it's only for offshore wells, very high production wells with big OD, because the minimum size is like 5.7. So it's 7-inch cased hole, or sometimes like 8-inch and 8.5-inch open hole completion, mostly. Sometimes maybe 6-inch open hole. Mostly offshore wells. Because of the price, you need a well with very high rate to make it profitable with this installation. And that's why there are not so many installations in general with this full electric valve. So maybe it's less than 100 wells just in all countries. Yeah. So the amount of these wells are not high because of the price mainly, and the OD is big. So, and there is another technology, the new one with also electric, full electric valves, but with a small size. So the size of the valve is starting from 3.5 inch. So with this 3.5 inch valve, you can install it inside 4.5 inch liner, which is so popular. Yeah, and you have so many wells like this. And you can install 3.5 inch valves inside with the packers and divide the well to sections and then produce and optimize your production. So if the water is coming from this zone, you just close the valve remotely. The price is much better than the full electric or even hydraulic valves of the Big Four. And yeah, this is the real photo of the valve. There is one limitation, and you need to understand it. So the size of the valve is quite small. So the OD is 3.5 inch. That's why it's no-go valve. Yeah. So there is no big channel to lock the well with the cold tubing. This is a limitation, but you cannot do anything with such a small size valve you need. So, but still the fluid can go through the valve, and practically, again, the question is, why do you need to lock this well? Yeah, you have pressure data, temperature data, you can close and open any valve remotely. So why to lock this valve? Huh? Some other sizes are also available, like 4.5-inch valves with bigger channel, inflow channel and through channel. So in each valve, there is a through channel through the whole valve, which is always open. And there is an inflow channel, which you can close, open, or just choke. And of course, the bigger size of the valve, like 5.7-inch valve, available. And in this valve, you have a through channel like 2.75-inch, which is like a must in for the many clients still. So to lock the well with the cold tubing and to have a full accessibility to the well. So you can control this valve on the well side. You have a control panel. You can open and close any valve or choke it to any position. Or much better way is to control it remotely. Yeah. So imagine this is your map and this is your wells. So some green wells showing that the water cut is low and everything is okay, and some red one showing that the water cut is too high. And you can remotely just select any well and just close or open or choke any valve you need. Yeah? This is really the remote control and the digital oil field everybody are talking about. So you save a lot of money, so you don't need to go to the well site to do any workover or whatever. You just control everything from the office. I think this is the future of the industry. I believe that more and more wells will be with some pre-installed sensors and valves and flow control devices, so you can control them remotely. Let me show you the case studies. So the first case is very simple. The short lateral horizontal well, 5.7-inch open hole, which was divided to two sections only, near zone and far zone. And the far zone was producing through the tubing and controlled by this valve. And the near zone was producing from annulus and controlling by these valves. So in this case, when you have only two sections, the valves are in vertical path. And it was found that immediately from the beginning, the water cut was 50%, which was more than expected. When the client closed the valve, it was found that the water cut in the far zone is 65%, which is a lot. And in near zone, 10% only. So the client decided just to close this far zone for several years and produce from the near zone only. For more than 3 years, the client got like 10% water cut only instead of 50%, so decreased the water cut substantially and increased the oil production. So the rod pump was working with the same rate, but the delta P was higher on the near zone, so the amount of oil production was almost doubled. And this was stable effect for almost 3 years. And the client was very happy and want to install this simple completion in like 110 wells right now. So you see, in this case, the client decided to close the section with 50% water cut only. Yeah, with like AICD, maybe the AICD will be still open because this water cut is low. Then the client decided to install more valves, like 3 valves, and divide the well to 3 sections with the 3 packers. By the way, the packers is also very important. How to set a packer properly in an open hole, because if you just set the swellable packer in an open hole, there are so many issues with the packers. They are leaking maybe in 30% of cases. It's difficult to put the packer in open hole. Yeah, you may have some cavern, so it's difficult. You may have some fracture, and the packer is small. Yeah? The size of the packer, the isolation part of the packer is like less than 1 foot usually, maybe 1 foot. So it's very easy for the water to cross the packer through the reservoir, just jump it. So in this case, initially, the expandable casings were installed in open hole. So the expandable casings are the pipes like this, of the same size like a tubing or liner, like 30-foot pipe. But the middle part of the pipe is profiled. It could be different profile, but still it's profiled like this. So you can install it on a drilling pipe. Then you just block this end and apply a pressure like 150 bar, and this pipe expands. So the metal is soft, it makes it round shape, and it's like a very big packer. There is also some kind of resin outside. So when it expands, it's like a very big packer. It could be like 50 foot. You can combine several sections together. It could be 100 foot, 150 foot, whatever you want. And you put this packer, this expandable casing, in a dense zones. So you lock the well with a caliper, find some section with low permeability according to your open hole data and stable OD, and then install this expandable casing. And even if you have some small cavern here, you have like 100 foot or 150 foot packer, this expandable casing. So for the water, it is very difficult to cross the whole like 150 foot section through the dense zone, dense reservoir to another like section. Based on the modeling, if this reservoir is like 100 millidarcy and this dense zone is 10 millidarcy, this packer is enough. So the water cut will never go to this section a lot. Yeah. So the water, if this water cut is 100%, then in the section 2, after several months, the water cut will be like 10% and no more. Even after like several years, it will be still 10%. Yeah, because for the water, it will be difficult to cross this very big packer and cross this low permeability zone. So this is the idea. And then if you install this expandable casing, this is like a small cased hole in your open hole. So it's much easier to install a packer inside. You can install a retrievable packer. So in this well, for example, the client, after a couple of years, retrieve the completion, the whole completion, and then check the valves and will install it in another well. So it's very cost-effective technology. And maybe the last case is the valves are also applicable not only in producers, but in injectors as well. So this is like 4.5 inch liner, a horizontal injector. So initially the client has 7 vertical oil producers, and the plan was to drill 3 vertical injectors to support the reservoir pressure. But then it was found that it is 1.5 times cheaper. The capex is cheaper to drill just one horizontal well, one horizontal injector with 3 valves inside. Even with the cost of the valves and everything, it's still 1.5 times cheaper to drill one horizontal injector. And the client drilled this well. The valves will be installed like in a couple of weeks from now. And this is like a small like smart field. Yeah. So you have pressure and temperature data in all producers. You have pressure and temperature sensors as well in each valve. So you can inject in this zone, for example, a pulse or some code. So like inject for 3 days, then stop for 3 days, then inject again, and see the response in the nearby producers. So you can do some pressure transit analysis, pressure tests, and all of them are like for free. Yeah, no need to install some logging tools or whatever. You just have sensors in your valves, in your completion. And this, all the hydrodynamic data are just for free for you. So you can optimize your injection, verify the permeability. This is a fractured reservoir, so you don't know really in advance. So what is the permeability? And the client doesn't know. Maybe you inject in the zone number 3, yeah, and suddenly get a very high water cut in this producer because of the fracture. So you can find all of this just because you have pressure and temperature sensors in valves and in oil producers, and you can change the injection in each zone, just closing and opening the valves remotely from your office. Yeah, so I think this is the future of the industry, just the smart field with all the sensors are pre-installed in a completion. Maybe the last slide is interesting about the prices. Let's say this is average prices. Of course, the prices are very different from different countries, but just average price is like, let's say, somewhere in the Middle East. Yeah. So for the ICD, different from different clients, but let's say like 100K, maybe 150K for section, including Packer and ICD. So for the AICD, it's a bit more expensive, maybe close to 150, depends on the client, but still quite expensive. The electric flow control valves is more than 1 million per section. So imagine you have like 5 sections. You want to divide your well to 5 sections, and you need 5 valves, 5 packers. You need to pay something like $7 million for this. So, and your well is like 10 million. So you need to increase the price for your well like more than 70%. Yeah, this is a lot. This is really a lot. For the hydraulic well, it's a little bit less, maybe, but not a lot. Yeah, it's still 800K, maybe not less than $500,000 per section. For the slim electric valve, the price can be as low like 200K per section. So you pay like 1 million for 5 sections well. With your price like 10 million for your well, it's like 10% increase, which is not a big deal. Yeah. Again, the OD is important. The OD of the ICD, I found some 4-inch, almost the same size of AICD. The electric flow control valves starting from like 5.7 inch, so only for big OD wells. But the slim electric flow control valves can be like 3.5 inch and installed in 4.5 inch liner, and even retrievable, which is a unique feature because mostly all the completions are permanent with swellable packers. So thank you for your time. Let's see how many questions we have. Oh my God, I think we have a lot of questions. Let me find what was the first question. Okay. How to minimize the gas oil ratio and water cut in the horizontal wells? So to minimize it, you need to install the flow control devices in your well. Let me go to the beginning. So for example, you installed the flow control devices in each section, and then you can open and close it. So if you have a high GOR in the section 2, you just choke the section, or if it's like 100% water cut, you just close this section. So I think everybody just got this, the main idea. So in the 7 developing horizontal wells, we installed AICD and plank pipe, and the interval with water is identified, but the water cut is up to 70%. The horizontal landing is also far away from the estimated water cut. Yes, this is the main issue. So AICD or ICD, they are based on your modeling and how accurate your open hole data. If you don't know really with high accuracy, and usually this is the case, you don't know the permeability with such a good accuracy, then you install the AICD and you are not really happy with this water cut. That's why you need the valve. So you need the valve which you can open and close at any time. Could you please briefly discuss the key difference with other market solution? Yeah, I think we mentioned this on this last slide. So first, the advantage of slim electric valve is that the size of it is very small. It's like 3.5 inch. So you can install it in 4.5 inch liner, which is usually very difficult for all other control devices. Usually you install these valves or even ICD in a new well. You need to put it as a part of your completion. But if you already have a well which was drilled a long time ago and you have a cased hole with
Okay, guys, Andre should be with you shortly.
yeah.
Yes.
So it was some disconnection, yeah. Okay, I hope you still can hear me.
Okay, Andre, let me take on the next questions from now.
Yeah, yes, please, yeah.
Okay, sure. Just after you're done. Next question is, could you please brief on the key differences with other market solutions?
Yeah, we just focused on this question. So the main advantage is the difference is the OD, so the slim electric flow control valves, and the size of any control devices you need for 4.5 inch liner should be like 3.5 inch. And such a size are not available on the market. Usually the size of the full electric valves like 5.7 inch, so you cannot definitely put it inside 4.5 inch liner. Another advantage and difference that this completion can be retrievable and put in another well because the packers are installed inside expandable casings, and usually the valves are installed using the swellable packers, so you cannot retrieve them, and if something goes wrong, you cannot retrieve the completion. It's forever. The remote control usually is a big question. With AICD on ICD, you cannot do any control. You install it as a part of the completion, and you cannot open it or close it or change the choke size. Never. You need a workover. And the price. The price is a very big difference for the price, and maybe this is so important with the current low prices. Maybe next questions.
Okay, so the next question is, what is the maximum flow rate possible through the slim electric ICVs as compared to hydraulic ICVs?
Yeah, this is a very good question. So for the 3.5 inch valve, if you have like 6,000 barrels per day, the delta P on the valve will be something like 1-2 bar only. So the size in the valve, the cross section for the 3.5 inch is like 1.3 inch. For the 4.5 inch valve, it's like 2.1. For the 5.7 inch valve, it's 2.75. So you see the difference in the through channel and in the inflow channel, but still it's quite a big hole. So if you want to choke any section, usually you choke it with a much smaller hole size. So it's applicable, I think, up to 6,000 barrels per day, which may be 90% of the market. Maybe next question.
The next question is, what are advantages over AICDs?
So again, the main advantage over AICD that you have a remote control. You can open or close any valve at any time you want. So for example, the water cut is like 70% and the AICD is closed. And you cannot open it again to produce, you block the reserves. If you have a valve, any valve, hydraulic one or electric valve, you can open or close the section when you want. Maybe you want to close it at 50% water cut when AICD is still open. And another advantage is that the AICD is working only when there's a big difference with oil and water viscosity. But sometimes, for example, in the Middle East, the oil and water viscosity are close to each other, like 0.3 centipoars, and this CD is not working at all. But again, the main difference is that you can open and close it. You can really control it with the valve, which you cannot do with ICD or AICD. Yeah, thank you. Maybe next question.
So I think the question pool is now ended. So
okay.
Thank you, Andre. If you guys enjoyed this webinar, then please put the thumbs up and subscribe. We have a lot of other exciting webinars coming later soon. So for all of that and more, I'll see you in the next webinar.
Yeah, thank you very much for your attention.